Hello and welcome. Thank you all for being here. My name is Dervis. I just want to say to you that this is my very first time in Stockholm, my very first time in JFocus, and the very first time I'm going to do the talk. So please be nice to me. If there's any feedback you might have to my talk today, I would love to hear your feedback. Please come to me later on and tell me if there's any improvements that you will like in this. So I'm going to tell you about my journey into the world of functional programming. This is something that started about a year ago. I work for the Norwegian government, and we have been having this, we have been transforming the government, moving to more agile sort of setting, where we also changed all, we gave developers more freedom, freedom to choose programming languages and new ways to build software. And using functional programming has been one of the things that we have been doing, and we have been looking into this. So when I started this, at least looking into functional programming, I basically had a couple of choices. I could use one of the hybrid languages, like Scala, Kotlin, or I could actually go with a purely functional language, because then you don't really have a choice. Because if you have a language where you can escape, sort of, say, do stuff object-oriented, then you really don't get the feel of how a purely functional language is. So when I started, or I got inspired by Disney. The way to get started is like quit talking and begin doing. So that's what I did. So in the beginning, it was like this. When I first looked at Haskell, I really felt like I was nowhere. I was kind of lost in the beginning. But as that time has been going and I've been looking into more and more into the language, I have been really seeing some similarities between all the new features that's coming in Java and what's already in Haskell. And I'm going to tell you more about this. I'm pretty active in the Norwegian community. I represent also the Norwegian JUG. I work in the government. So this talk is not about all these things. I'm not here to evangelize Haskell in any way. So I'm going to keep it very simple and introduce you to some of the basic concepts that you can learn from and bring into your world if you are a Java programmer. So I will start with a brief summary of what I have learned. So here's a lot of bullet points, but a couple of the more important stuff I would like you to know is that Haskell is actually garbage collected. I will show you how this works, and it's lazy and immutable by default. So there is not an easy way to actually to mutate data in Haskell. And Java, on the other hand, as you know, is mutable. It's statically typed and strict. Strict means that all the functions is actually first evaluated, and then it's passed on to different functions. There's a couple of names I want you to note here, especially in the Haskell community, because there's John Hughes and Lennart Augustsson from Chalmers University. They are two Swedish professors that actually contributed to the development of Haskell. So this is quite interesting thing. And I will also like you to note Philip Weidler. He's one of the guys that introduced generics in Java. So there is pretty interesting names that you can look up. So Java is really about clear and readable and reliable code. And Brian Getz, the language architect, he's saying that it's important to make it easy to build and maintain code and write reliable code. That's why people keep using Java. So it's not really a goal in itself to shrink everything or abstract everything so much that it becomes unreadable. And we see a change in Java because Java is getting record syntax, seal types, value types. I will show you examples of what those are in very shortly. Pattern matching and switch expressions. All of these changes in the Java language is pushing the language in a more functional direction. So Haskell. Haskell is strongly typed. It has a very, very powerful type inference. You get a lot of syntactic sugar by the language. You'll see this in a moment. And Haskell hasn't really had the best tooling support, so it has been very difficult to actually just start using it. But the thing that is happening now is things are changing. The tools are getting better, and the industry is growing, such as in the Norwegian industry. We have one of the biggest ad search engines, which is using Haskell for their backends. In the Norwegian government, we have tried using Haskell for about 5 or 6 of our backends. So far, it has been going good. The challenge is, of course, building up a community around this. But by looking into it, we are hoping to at least interest or inspire more people. So Haskell is lazy and is immutable. So that means there is no easy way of doing side effects in Haskell. And the language is mostly about expressions, and an expression always results in a value. And values in Haskell is first-class citizens in the language, meaning that you can pass them around. And the language is quite flexible because there's a lot of features of Haskell that you can enable and disable. These are called pragmas. You can enable them on the command line or per file. So let's look at the compilation and runtime systems first. This is Java. It might be familiar for you. The source code is read into the compiler. The Java compiler doesn't do very much besides parsing, and it creates the bytecode. Later on, the bytecode is read into the JIT compiler, and when your program is running, you also have the hotspot VM optimizing your code further, and if necessary, generating machine code. And this is Haskell. A slight more stuff is happening here. So you have the Haskell source code. It's read into the Glasgow compiler. The Haskell compiler is generating something called core. And core is a tiny functional language itself, and it's really only used for optimizing your code and desugaring your code and so on. From that stage, it turns into something called STG. This is very similar to core, and this is where the code generation is starting. So from STG, it goes on and becomes C++. It's actually called C++. And C++ is a subset of C language. So it's very similar, and from this point on, you can basically choose what you want to generate over here. C code, machine code, LLVM code. You can choose the these are called backends. The writers of the Haskell compiler has written an amazing article describing all the details of the Haskell compiler. It's written by Simon Payton. It's a very good article that I advise you to look at if you're interested in the details. So the Java runtime system, your class file is read in to the VM, and the execution engine will map this, and the heap, the registers, and, well, what you are doing basically is your source file is read into the VM. Haskell is slightly different, because when you compile a Haskell program, what you are getting is a binary file, executable file that you can run. So here, the opposite thing is happening, because Haskell has a virtual machine itself, but that virtual machine is really compiled into your binary file. So your source code and the compiler libraries, they are all compiled together, and is mapped and run together with the Haskell execution context. This is the threading library that Haskell has, which is mapping all the cores of your your CPUs and hardware, and it's basically running everything inside. So this is a very simplified model. There's a lot of details I'm skipping here, but your source file is read into the VM. In Haskell, the runtime system is compiled down together with your source files. So some important differences. This is by far the most important difference here, because Haskell guarantees immutability. Every time you change something, every time you change a list or a data type or whatever you change, it's going to be another copy of it. So that's immutability. It simply means that you cannot change data. You cannot mutate data in place. There is something called dirty code. Dirty code means basically mutated data or input from outside, such as input, output, file handling, and so on. These are handled in something called I/O monads, which is out of scope for this talk. But so I talked to one of the participants yesterday, and he asked me a question. He said, "Do you know why Haskell programs never fail?" The answer is because Haskell programs never run. Well, we have to run our programs. And to do this, we need impure code. Impure code is written in monads. Monads are used to, for example, handle input from command line. In the Haskell world, this is called sequencing. Sequencing here in this context means that every line is evaluated in order. In the first example over here, you can see I have a function that concatenates the input. What you really should do in this example is extract the concatenation and basically make a separate function of it and make it referentially transparent, meaning that you can change this anywhere in the code that uses this function, and it will always be the same result. Lazy evaluation. Lazy evaluation means that when you pass around functions, Haskell doesn't really execute and evaluate that function right away. It will delay the execution of the functions. And at some point in the future, if Haskell finds out, well, I don't need to evaluate this and that function, you save time and you save processing, and you can optimize the code. So I have a code example. I borrowed this code example from the legendary Venkat Subramaniam. He showed an example, basically having some print lines over here. It's a simple if statement. If the if statement will be okay, then you print result, otherwise no result. I have a compute method over here. It's this one. It basically doubles the number. And yeah, so when I execute this one, it might be small text, but it says called here and no result. So called is printed inside the compute method, so you know for sure that the compute method was called. And then it prints here, and then no result. So how do we learn from Haskell then? How do we make this lazy? You can use something that is called a supplier. I will show you how this works very quickly. We put it here. And then instead of this one, this, now we have to change this one because now it's a supplier. So we say get. What do you think will happen now? Well, let's see. It didn't call the compute. as it turns out, when Java is evaluating your function now, it sees that, it's not necessary to execute this one. It's a lambda, so the function is not called because the text is not there. If I, however, I make this statement true, you can now see another thing which is interesting. It's called here first. This line is printed out first, and then when it's necessary to get the value, it evaluates the function. So this is getting this sort of feeling to how a lazy evaluation works. This is something that you can learn and get some inspiration from Haskell. The code, the source code, is on this link. My slides are online. You will get the link afterwards. Okay, so some basic types. In Java, we have double, long, int, and these are called primitives in Java. In Haskell, well, it's more complicated over here, but in Haskell, you do have primitives, but the primitives are not really recommended to using, because by using the Haskell's primitives, you are making sure that you can introduce bugs. In Haskell, you have int, integer, double, and float, bool, bits, and char, and string. You don't have any long. You can see how it compares. Byte is actually int 8. These are signed integrals. You have the unsigned versions of these ones also. So byte, this int 16 will be short, and so on. So int in Haskell by default will be the 64-bit version of it, so long. And integer over here, integer is the unbounded type. Unbounded type means that you can represent any number, basically, any large number. So this is how it compares some stuff. Haskell will optimize your code itself, so no need to use Haskell's primitives. Because by doing this, you cause eager evaluation, and eager evaluation makes sure that you will make it much more difficult for the compiler to optimize your code further. If you want byte manipulation, you can do this. It's not that obvious, but you have to import data bits, and you have to also enable an extension here. But it is possible. Arrays, each of the lines compares to each other. I'm not going to go into detail. What you're seeing here is called list comprehensions. I'm going to show you a quick example how it works. But Haskell's arrays are lazy and it's immutable. Haskell does provide mutable arrays. You have something called STU array, which is immutable. They are very flexible. It would probably take an entire talk itself to cover just Haskell's arrays. Everything that you can do with arrays is contained in the data array module. I'm not going to go into detail. The source code is online. I'm just going to show you one very interesting thing that you can do with Haskell's arrays. If you take a look at this line, this is a list comprehension. It produces an array. But inside here, you see something interesting, because in Haskell, you can actually choose yourself what the indexes are. The indexes in Haskell arrays don't need to be integers. They can be chars. So I have been playing around with making a chessboard over here, and I chose to represent with the letters. So when I run this, down here I have another version with two-dimensional arrays. You can see that it works. And I'm using the letters as indexes. So this is quite interesting thing that you can do in Haskell. Okay, moving along to algebraic data types. How many of you has coded in Haskell? Wow. If I do any mistakes, sir, please come to me later on, okay? These are called ADTs for short. So algebraic data types is categorized into two things, sum types and product types. So sum types, this is something that can be one of several things in a set. Example of this is enums, algebraic data types with several constructors. And there's a small catch with the Java enums over here. I will show you. The product types can be records, tuples, algebraic data types with only one constructor, Java classes, C structs. And the catch with the enum in Java is that you really cannot extend it with additional data. Here's a simple example. I used enum in Java for this example. This is pretty much the same thing, which is written here. This is enum type in Haskell. It's separated by the pipe, as you can see. And this pipe basically tells that animal can be one of those types. Dog, cat, elk. I also, as you can see in the Java example, I added a property. You can do the same thing in Haskell by basically providing the type after the data constructor. So dog, cat, and elk are data constructors. Animal is type constructor in Haskell. And then you can see I have three functions. What I'm doing over here actually is pattern matching in Haskell. So I can decompose the type, and I can match each. If I had several types, I will show you next, I could match each individual property. This is harder in Java. Another example, this is Haskell, and this is the difference, big difference in a purely functional language. In Haskell, your data types can actually have multiple constructors with different data constructors and parameters. So you see string, string int double, and I have another one called unknown. This is called nullary type. It does not have any additional data on it. And then you see the same thing. You have the pattern matching, the info function, the underscore over here is, it means that we ignore that parameter. We match on the second one, and you can see how I'm using it. This is basically otherwise. If it doesn't match on the three first functions, it will default to this function. So in Java, very soon, we will have something called records. These will have named accessors. So let's take a look. And it will, by the way, it will come from Project Amber. So it's just around the corner. So Java 14 records. This is more like we are moving towards similar stuff from Haskell. This is how it might be. I'm not sure if it's going to be like this, but it's record, animal. You see the three different properties. Animal type is an enum. It can be one of them. And you can see the named accessors that I told you is these three. This entire code example is online, and it works. There is a couple of things that you have to do to get this working. But it's here, and you can run it, and you can test, and you can play with the records. Haskell's record type is basically this stuff I have in here. So instead of having the enum type, I basically have a record syntax. In the record syntax, I also apply the type of each property. So string, int, and I define the animal type. And I'm also extending the show type here, so I can actually print out info about my custom type, and I can use it like this. And again, you see the name function over here, because Haskell has now in the background automatically created those accessors for you. The source code is here. In Java 8, I checked around a little bit. There is a couple of libraries. The two lower ones are actually not maintained anymore. I don't recommend them. Spotify has something called data enums. These are under the hood based on some techniques that Philip Wadler, one of the creators of Haskell, he wrote an article about this, and he's talking about the expression problem. And if you read Philip Wadler's article, you will find out why it's not a very good idea to use these libraries yet, and it's better to wait for Java 14's record types, really. There are some maintainability problems here and some other challenges. There is also another nice article that I can recommend reading about some types. So continuing Project Amber. Seal types. Getting seal types moves us one more step closer to getting the real benefits of algebraic data types. This is, I took this from the JEP, basically, so it might change in the future. But what it basically is doing is saying that if you have an interface, you can have more control over which classes actually implements this interface. You can permit, and if you want to understand how what this actually is, we can illustrate this in Haskell, because in this example over here, I have a class type. A class type this is what's closest to interface in Java. So I call this automobile. It's a parameterized type. It specifies that everyone that extends this has to implement the spec function. So I did exactly that. It's called instance in Haskell. When I extend automobile, I also have to implement those functions. But here you see something interesting, because I have done this 3 times. I have overloaded the spec function to cover each and every data type: car, bus, and plane. And when you do this, Haskell makes sure that your code is type safe. There is really no way to introduce an unknown type that might cause some side effect anywhere. Because in Java, you have the possibility that if you have an interface anywhere else in the code, that can be extended and introduce some other function that might do unknown stuff. So this is the important thing in this, that you can actually bring into Java and to understand how this really works. Inline classes in project Valhalla. This is a quote from Brian Getz. Calls like a class, acts like an int. What exactly this means is that when you apply, and this might also maybe change, but it simply means that your type is represented by its value. So it's not like normal objects, which is represented by a pointer to an object in the heap. This is not how that's going to work. It's going to be all about values. And when we move a language towards values, we can also introduce much more powerful pattern matching and so on, features that you can learn in Haskell now. In Haskell, out of the box, everything is values. So this actually already, Haskell is like this already. Everything that's written in JEP 169 actually does apply to Haskell. There's a couple of mutable types in Haskell that this, of course, doesn't match with, but all other data types is already by default about values. And I recommend reading Brian Getz's own article. It's The State of Valhalla, I think it's called, is on this link, explaining this much better. Okay, so modules. One surprising thing is that in Haskell, indentation matters. Braces and semicolons are optional, because in the code examples so far, you have seen that there is no braces and there is no semicolons. In Java, spaces and tabs are ignored, but braces and tabs are required. So this is I have some code examples in my repository that you can look at. Java class, familiar, 2 functions. In Haskell, you define a module like this. I have two functions. This is one way of doing it, but this is actually anti-pattern in Haskell. So the correct way the recommended way of doing it is also adding the type specification, the declaration of the function. And by doing this, you can actually tell your fellow developers what this function is actually doing. So it's one way of documenting your code. Imports. In Java, you have Java lang imported by default, and in Haskell, you have prelude, which is imported by default. And import static, you can do the same thing in Haskell. And one really big difference between Java and Haskell here is this import qualified, because why would you need to do this? Because in Haskell, you have different modules. They have some functions that exist in several modules. But because of how namespacing works in Haskell, you get name collision. So when you import qualified, you can import it as a prefixed name. And then you can, every time you want to call a function that also exists in another module, you can prefix it with that letter and access it. Okay, so in Java 9, we had the Java module system. This is all the possible stuff that you can use in order to control what is visible in your modules. In Haskell, and this is not exactly direct matching, so I'm just pointing that out, because what I'm really showing on the Haskell side here is what you would otherwise use public, private, and those accessors. But I want to show what is the similar here, because by using in between the parentheses here, you can control what every other module is seeing from your module. So what you can basically do is you can make sure that your interface, your API is exported and visible, and you can hide the implementation details, because later on, this gives you the freedom to change your implementations detail while keeping the API intact. So I tried to convert Haskell code over to Java code, and I started with a type class, a parameterized one. There is a catch over here that I'm going to show you, because in the Java side, I used a generic type, and I have basically tried to do the same thing. There's a very important thing that we have to learn from this. Here is a complete example. I basically took this type class and I implemented in Java. And if you take a look over here, you can see that the student class implements person. And when I implement person, you can see that I have to implement the name method. But now, what you see here is this function actually, as the interface says, you have to use the generic type. So I have to also add the student here. But the student class itself is an object that represents a student. So why do I pull in another student object here? So this causes low cohesion in your code, and it's really not the idiomatic way of doing Java programming. And then I tried to convert the instance types. Well, you get the same problem. So what would be the correct way of doing this? Well, in Java, the better way to do this is by not using the generic type over here, because then you can encapsulate information about the student in the student class, and you basically return information from within this object. Everything is online. You can try it. Control structures. I'm going to go quickly through this. It represents a person that has a salary and tax class. Ifs is pretty much the same, with one exception, that if statements is expressions, has to always result in a value in Haskell. So else is required. Else if is the anti-pattern in Haskell. So Haskell has something called guards. That is another way of writing this. Here I'm repeating this operation 3 times, so I can further improve this by adding a where clause over here. Now I have one expression telling what I'm actually doing, and you can have pattern matching and check what the values are. Switch case in Haskell and Java, there are some similarities. In Java, of course, this is not expression, this is statement. So you can cause all sorts of side effects. In Project Amber, in Java 13, switch expressions came along. And this is a very, very nice thing that I'm using it. And another thing that Java has that Haskell doesn't have is multi-case matching. I was very surprised to find out that this is actually not possible in Haskell. So I had to hack my way through to try to get the same function over here. If anyone knows about a better way to do this, please let me know. But I use a function, and I check if this letter is in this set over here, and you get the same thing. I will skip this. This is online. So finally, functional programming. Why hasn't functional programming taken over the world? Why hasn't Haskell got more spread? Why isn't that? What isn't used? I'm going to start by mentioning object-oriented programming, because object-oriented programming has been very, very successful in terms of being adopted by the industry. If you go back in time, all the way back to Algol 60, which was one of the very first procedural languages that inspired nearly every other language that exists, and Simula, for example, which was developed in Oslo, which further again inspired a lot of other languages. And I do want to mention Unix, the operating system. There is a whole chain of effects here bringing the object-oriented languages closer to the industry. Functional languages has mostly been academic languages that is mainly used for proving mathematical models and so on. But the more important things over here is marketing, because Java has been very, very extensively marketed. I've tried to find some examples over here. Tooling is extremely well supported, and not to mention library support. Haskell has a couple of versions now that you can actually use in the JVM. One of those is called Fredge, and another one is called ETA. You can run Haskell on the JVM, and the point of this is actually getting the same tooling support. Performance, if you attended a couple of talks yesterday, Raphael's talk or David's talk, you will understand that JVM is amazing. And it's attracting a lot of languages to actually run their code on the JVM. Time to production. This is something we saw in the government as well. It takes time to learn Haskell. It's easy to get started. It's easy to see the same patterns that I showed you here today. But in the first slide, all those other types, higher order functions, function composition, monads, these things makes it difficult to master the language. Java, on the other hand, you can get something out very quickly. The most important one, and this is, for me personally, very important, the community. Java is really a worldwide, is developed by many, many, many volunteers and people basically improving this language every day. This is something that we are very lucky to have in the Java community. And I'm pretty sure this alone is going to make Java be still used in many years to come. So I mentioned Fredge and Etalang. These are alternatives that you can use. My slides are on this link. The code is on REPL. I'm going to tweet the links for you. This is my tweet handle. If you have any feedback, please come and tell me. I really want to improve. I really want to get better at this. And that's what I had. Thank you so much for being here.